So, let's say I want to throw this 1 Newton apple, which is, it says 1 Newton on it.
Echoing.
I want to throw this to Cohen. Okay? Am I going to do work in throwing the ball to Cohen?
Yes.
Am I going to exert a force over a distance?
Yes.
Yes. Okay? So I did a certain amount of work, right? So, now, Cohen, throw that back. Hold on a second. Where did the force go? So aim for the hand. Now, if I don't catch it, okay, does the kinetic energy of the apple change?
No.
No. Okay? Because of the fact that without work being done, there's no force acting through a distance. There's no force acting through a distance. There's no change in velocity. No change in velocity. You don't change kinetic energy. So, one of the things you'll see is that a whole bunch of things are going to begin to set equal to each other. So work can equal force times distance. It can also equal a change in energy. And that change in energy could be the change in the kinetic energy, which could be kinetic energy final minus kinetic energy initial, which you could write as 1/2 mv squared minus 1/2 mv naught squared. And if you wanted to get clever, you could write that as 1/2 m times v squared minus v naught squared. So here's the question. If I take this apple and if I just hold it here, I'm not going to change the kinetic energy of it because I'm not going to do any work. But if I want to change the kinetic energy, I have to do work. Now, if I just give this a nice toss, okay, do you think I did much work?
No.
No, okay? I didn't exert much force over a distance. Now, throw that back. Now, I'm not going to do this, okay? But let's throw I wound up, boom, okay?
You should.
Threw it really, really hard, and my arm traveled through a big distance. What would happen to the amount of change in kinetic energy?
It would increase.
It would increase, okay? So let's look at a simple example. So, let's say we've got mass of 10 kilograms, and let's say that it's moving at 6 meters per second. Boom, we're gonna make the car stop. Did the kinetic energy of the car change?
Yes.
Yes. Why, Preston?
Because it went from moving to not moving.
Yeah, okay, there was a change in velocity. Oh, change in velocity implies an acceleration. Acceleration implies a force, right? So, I can calculate the initial kinetic energy, which is going to be 1/2 mv squared. So I got 1/2 times 10 kilograms times 6 meters per second squared. That's 36, 18, 180 joules. Now, an interesting thing happens. If I double the velocity, what happens to the kinetic energy? It goes up by a factor of
4,
4. Why?
because velocity
Squared.
squared.
It's velocity squared. If I double the mass, what happens to the kinetic energy?
It doubles.
It just doubles. So changes in velocity have a much bigger impact on kinetic energy than mass does. So if you're driving along in your car at 10 miles an hour and you speed up to 20 miles an hour, how much does your kinetic energy change? You went from 10 to 20.
Times 4.
Yeah, times 4. You go to 30, you go from 10 to 30,
Times
Times
6.
Times 9.
Wait, 9.
Nine.
Wait.
Be
10
3 times, so yeah, 9.
3
Or-
squared is 9. So
Yeah.
9 times.
yeah. So, and that was the
My
argument
math is
when they began to raise the speed limit from 55 back up to 70. Physicists are going, look, kinetic energy is what causes damage. And if you increase that velocity from 55 to 70, that isn't a linear increase in the energy of the cars. It's a quadratic curve. So small changes in how fast you let cars drive isn't this like, oh, they'll go twice as fast, we'll have twice as much energy. No, that's going to increase by a factor of 4. So, at this point, can you calculate the change in the kinetic energy?
Yes.
Yeah.
And what would that change in the kinetic energy be?
Be
Four.
negative 180 joules.
Negative 180. Why?
Oh, because you
Because
had
it's final kinetic energy
Yeah,
is 0
so
minus
one way you
the
look
initial.
at changing kinetic energy is 0 minus 180. Check my math. You get
Negative
negative
180.
180.
180 joules. Now, was there work done on the car?
Yes.
Yes. How much work do you think was done on the car?
180 joules.
Nope.
Negative 180.
Negative 180 joules. Okay? Now, let's say at this point, do I have enough information to calculate the force acting on the car?
Yes.
No.
No.
Nope.
We don't know distance.
I don't know
No
distance, because work equals
FD.
FD.
FD. Now, if I said that the car slows down over a distance of 20 meters, then could you calculate the force?
Yes.
Yes.
Because now, on a force distance graph, so that force, that area, is going to be negative 180. So this actually needs to be like 0 joules. So, because the area underneath is going to represent, that's going to be 0 newtons, not joules, 0 newtons. So, the force is what we need to find. If the distance is 20 meters, how does that 180 fit in with that force distance graph?
You divide it by 20.
No.
Area.
That's the area.
That's the area.
Okay.
To get the force, what are you going to do?
Divide by 20 meters.
Yeah, so if I take negative 180 joules and divide that by 20, I get
Negative 90 newtons.
negative 90 newtons. So kinetic energy itself cannot be negative, but you can have a negative change in the kinetic energy, okay? And that's the big difference between the two. So, let me hand out the assignment right quick, because time is running out.
Why is this hurting so bad? I don't know. My elbows have been
Okay,
just.
so when you get to question number 9, okay?
Bold of you to assume I'll make it that far.
So you got to go old school on question number 9.
It'd be like if you finish this.
And how do planets orbit around the sun? Circles or ellipses?
Ellipses.
When do they travel fastest?
When they're closest to the sun.
They're closest. So when do they have the most kinetic energy?
When they're
When they're
closest.
closest.
Keep that in mind when you answer question number 9. When you get to question number 10, 10, you kind of got to go old school. I gave you the force, I gave you the mass of the ball, it's in contact with the racket for 0.03 seconds. What's the kinetic energy of the tennis ball? At the end of the day, you got to use 1/2 mv squared. Okay? The trick on number 10 is that you have to find the velocity to put in there. When you get to question number 11, do not flip out if you have the same answer again and again and again on number 11. Because just like we worked, I said, oh, what's the work done on the train? Oh, you know the force and the distance. Okay. What's the change in the kinetic energy? Oh, change in kinetic energy equals work. What's the final kinetic energy of the train? Well, the initial kinetic energy of the train is 0. So that's why I said, because there's so many things that you can set equal on this work energy side, if you get the same answer again and again and again, don't flip out. because so many things are equal to each other. So, all right. There you go, kids.
Goodbye.
So shut down yonder camera.